These are examples for section 6.2 parallelograms. Example 1. A parallelogram exists in the structure of the lamp shown at the right. What is the measure of angle P in parallelogram PQRS? So taking this first part here, this part of the lamp is a parallelogram. The lamp or bulb is right here. Notice angle P is what they're asking for, the measure of this angle right here. The only other angle we have is the measure of angle S, which is 64 degrees. Notice that in the parallelogram, angles P and S are consecutive angles to each other. And according to your notes, consecutive angles of a parallelogram are supplementary. So we can say, according to that, the measure of angle P plus the measure of angle S, consecutive, equals 180 degrees. Taking the measure of angle S, 64 degrees, we have the measure of angle P plus 64 degrees equals 180 degrees. Subtracting 64 degrees from both sides, the measure of angle P is 116 degrees. There's our first answer. So this is 116 degrees. The second part of the problem, if the lamp's position is adjusted to where the bulb is closer to the flower by 5.5 degrees, what then will be the measure of angle P? What then will be the measure of angle S? So what's happening here is you pull this lamp or globe down closer to the flower, the shape of this parallelogram is going to change. If this is the original position, there's angle P and angle S, and we pull the lamp down this way, you get something that looks like this. Notice that angle P, as you pull this down, this angle right here, is getting smaller or larger? It's getting smaller. And according to this problem, it's been pushed down enough for 5.5 degrees. So we take the measure of angle P and we subtract 5.5 degrees. So new position of the lamp after the adjustment, the measure of angle P, its original position, minus 5.5 degrees. So that would be 116 degrees minus 5.5 degrees, which gives us 110.5 degrees as the measure of angle P. This is the new position. And then for the measure of angle S, notice that the measure of angle S, 64 degrees here, as this gets pulled down, we go from this angle to something that looks more like this angle. Notice that the angle is getting larger as this is being pulled down the lamp. So we're adding 5.5 degrees. So the measure of angle S is 64 degrees plus 5.5 degrees gives us 69.5 degrees as the measure of angle S. This is in the new position. So these two are in the new position and 116 and 64 at the old position. Example 2. Find the measures of the numbered angles in the given parallelogram. We go back and use any of the theorems, postulates, definitions, and any new ones that we've learned about parallelograms here. First of all, we've got 75 degrees on this angle right here, and 50 degrees in this angle right here. I'm going to start with the measure of angle 2. I noticed that the measure of angle 2 and the 75 degree angle are both, or they both create a linear pair. So by the linear pair postulate, measure of angle 2 plus 75 degrees must equal 180 degrees. Right here, these two. So the measure of angle 2, subtracting 75 from both sides, we get 105 degrees. So the measure of angle 2 is 105 degrees. Next, I'm going to focus in on angle 4. Now I could use another linear pair, but I'm going to use vertical angles here. Vertical angles are congruent. Vertical angles congruence theorem. So by vertical angles congruence theorem, the measure of angle 4 is equal to this measure here, 75 degrees. So the measure of angle 4 is equal to 75 degrees since these two angles are congruent. Angle 4 is 75 degrees. Then I turn my focus to angle 3. Now that I have angle 4's measure and I already have this angle in this triangle right here, by using the triangle angle sum theorem I can find the measure of angle 3. So by triangle angle sum theorem, we have the measure of angle 3 plus the measure of angle 4, which is 75 degrees, plus the measure of this angle, which is 50 degrees, must equal 180 degrees. Triangle angle sum. Combining these terms, we have the measure of angle 3 plus 125 equals 180. Subtract 125 from both sides, and the measure of angle 3 is 55 degrees. So the measure of angle 3 is 55 degrees. Finally, we have the measure of angle 1. Notice that the measure of angle 1, since this is a parallelogram, opposite sides are parallel by definition of a parallelogram. Since these two sides are parallel, in addition to these two, if we extend these two lines, these two sides, and extend this line right here as a transversal, notice that these two angles here, angle 3 and angle 1, are what kind of angles? Alternate interior angles. So by the alternate interior angles theorem from a long time ago, the measure of angle 1 must equal the measure of angle 3, and therefore, since the measure of angle 3 is 55 degrees, the measure of angle 1 is also 55 degrees. Again, the theorem says that if two parallel lines are cut by a transversal, alternate interior angles must be congruent. Example 3. Solve a linear system of equations to find the values of x and y in parallelogram KLMN. This one right here. Notice that the two diagonals are drawn for this parallelogram. It is a parallelogram. And we learned in our lesson that the diagonals of any parallelogram must bisect each other. So if the diagonals bisect each other in this parallelogram, that means LP must be congruent to PN, and PM must be congruent to PK. Knowing that, we can set these two equal to each other and these two equal to each other, creating two linear equations with two variables. So, by diagonals of parallelogram bisect each other, we can come up with, first of all, LP, the length of LP must be equal to the length of PN, and the length of KP must equal the length of PM. Substituting in the algebraic expressions for each, we starting with LP, we create our first equation. LP is x, and it's going to equal PN, which is y plus 2. Our other equation comes from the other diagonal. KP, which is y plus 10, must equal the length of PM, which is 2x minus 8. Now we have two equations, equation 1 and equation 2. Both have two different variables in them. Recall there are several ways to solve systems of equations that you learned in Algebra 1. Most of the time we will be using only one of those methods, substitution. You use substitution when you notice that there's a variable that it has 1 as a coefficient and it's by itself, or we can get it by itself. For instance, the x here is by itself. The coefficient is 1, and so x has been solved for. When this happens, it's much more convenient to use the method of substitution. So what we can do is we can substitute equation 1 into equation 2. So since x is y plus 2, then in the other equation, it has to be the other one, wherever we see an x, and in this equation we only see x once, but in this equation, wherever we see an x, we substitute in what x equals. X equals y plus 2. So the y plus 2 will be entered or substituted in right here. So when we do that, we get y plus 10 equals 2 times x, which is y plus 2. Back to the equation, minus 8. Notice there are no x's in the equation. Everything is just in terms of y. So now we solve for y. Y plus 10 equals, using the distributive property, we get 2y plus 4 minus 8. Combining those terms, we get y plus 10 equals 2y minus 4. To solve for y, since we have two y terms, I subtract y from both sides. Over here, I get 10, and then 2y minus y is 1y, or y minus 4. Adding 4 to both sides, I get 14 is equal to y, or y is 14. So we found one of our variables. At this point, once you found one of the variables, it doesn't matter which of the original equations you substitute that back into. Most students like to choose the equation that seems simplest, so we'll do equation 1, but you should be able to substitute it in equation 2 also. It doesn't matter which. So we write substitute y equal 14 into equation 1. So I take equation 1, and everywhere I see a y, I replace it with 14. So that's x equal 14 plus 2. So x is equal to 16. We found both of our variables. The second part of the problem says, what are the length of km and the length of ln? Km is one of the diagonals, ln is the other one. So starting with km, we take these two expressions using segment addition. We add these two expressions together to get the whole segment, or the whole diagonal. So we have kp, which is y plus 10, plus, we add this to it, 2x minus 8. Then we substitute in our x's and y's. So km is equal to y, which was 14 we found to be, plus 10, plus 2 times 16 is x minus 8. Order of operation tells us to multiply first, so we have 14 plus 10 plus 16 times 2 is 32 minus 8. We add and subtract from left to right. 14 plus 10 is 24, and 24 plus 32 is 66 minus 8. So km is 66 minus 8, which is 48. Oh, excuse me, this is 56, not 66. 56 minus 8 is 48. And then for the other diagonal, ln, do the same thing. ln is the addition of these two segments, x and y plus 2. X plus y plus 2. So substituting in x and y, here we get 16 plus y, which is 14, plus 2. That gives us 16 plus 16, which is 32. So the length of diagonal ln is 32 units long, and the length of diagonal km is 48 units long, and we wouldn't have been able to find them without finding x and y. Example 4. For what values of x and y must quadrilateral PQRS be a parallelogram? So what they're saying is, they're asking what values of x and y should these be to cause this to be a parallelogram and not just some quadrilateral. Well, we still use the properties of parallelograms. After we find x and y, they want us to find the length of PQ here and the length of QR here. So not only are opposite sides of a parallelogram parallel by the definition, they're also congruent. So opposite sides of parallelogram are congruent. Using that property, we can say that PQ here is equal to the length of SR, and we can also say that PS, the length of that, is equal to the length of QR. Substituting in those values for PQ, we get 4x plus 9 equals SR, which is y plus 10. Our other equation right here, PS equal QR, we take PS's length, which is 3x plus 8, and set it equal to the length of QR, which is 4y minus 1. So here are our two equations with two unknowns, x and y. Again, using substitution, notice that there is a variable in one of these equations that is, can be set by itself pretty easily, and that's y. It has 1 as a coefficient. So if we can get y solved for here, which is pretty easy to do, if we subtract 10 from both sides of this equation, we get 4x. Subtract 10 from plus 9, we get minus 1 equals, and then y. The 10 goes away when we subtract. So y is equal to this expression in terms of x. Now we substitute this expression everywhere we see a y in this other equation. It has to be the other equation. So right here. So substitute equation 1, solve for y, into equation 2. So starting here, we have 3x plus 8 equals 4 times this expression for y, 4x minus 1. Back to this equation, minus 1. Notice everything is in terms of one variable x. Now we can solve for x. Using the distributive property here on the right side, we have 3x plus 8 equals 16x minus 4 minus 1. Combining like terms on the right side, we get 3x plus 8 equals 16x minus 5. Having an x term on both sides, we subtract 3x from both sides. Over here, they subtract out, and we get 8 equals 13x minus 5. Adding 5 to both sides to get rid of the minus 5, we get 13 equals 13x. Dividing both sides by 13, we get x equals 1, or 1 equals x. So we found our x value. Now that we have that, it doesn't matter which original equation we substitute this into. We can even substitute it into this one. So this is a form of equation 1, so we're going to substitute x equal 1 right here into equation 1, which you can either use this one or this one, it doesn't matter. I'm going to use this one. So we have 4 times x, which is 1, minus 1 equals y. Here. 4 times 1 is 4, minus 1 equals y. And so 3 is y, or y is 3. So we found our other variable. Now that we have both variables, we can now find the length of PQ and QR. So PQ is 4x plus 9, where x is 1. So substituting that in, 4 times 1 plus 9 gives us 4 plus 9, which is 13. And so PQ is 13 units long. And of course, so is SR, because opposite sides are congruent. Then we go to find QR. QR is 4y minus 1. 4y minus 1. Substituting what we found for y, 3, we substitute that in for the y. 4 times 3 minus 1, which is 12 minus 1, which is 11. So QR is 11 units long. So is PS, because opposite sides are congruent. We could even find the perimeter of this parallelogram at this point if we wanted to. Example 5. For what values of W and Z must quadrilateral ABCD be a parallelogram? Then find the measure of angle B and the measure of angle C. Put this video on pause, and then when you're ready, turn it back on to play to see if you got the right solution and answer. Okay, to start off with, notice that we have all 4 interior angles. What do we know about angles of parallelograms? We know 2 things. Opposite angles are congruent, and we also know that consecutive angles are supplementary. So we have a choice at first anyway. Notice that some of the expressions have Z in them, some of them have W in them. Most students are going to want to keep the W's in one equation and the Z's in another equation instead of having to use a system of equations. Let's see if we can do that. We can. If we use opposite angles are congruent, notice that angle D and B are opposite each other and they both have a W variable in them. And A and C opposite each other, they both have the same variable Z in them. So that's probably the way most students would choose to do it. That's the way I'm going to do it. So we're going to use the fact that opposite sides or angles are congruent in a parallelogram. So since opposite angles are congruent, let's make our initial statement. The measure of angle A must equal the measure of angle C, and the measure of angle D must equal the measure of angle B. Taking those expressions for those those angle measures, I'm going to go ahead and start with the measure of angle A and C. So right here, substituting in those values, I have 7Z plus 5 equals 8Z minus 10. And then for this expression, the measure of angle D equal the measure of angle B, I take these 2 expressions, and I have the measure of angle D, which is 5W. D is 3W. 3W plus 10 degrees equals the measure of angle B is 5W minus 30 degrees. Now we can solve this equation by itself and solve this equation by itself and get both values of Z and W. So starting over here, I can subtract 7Z from both sides. And over on the left, those they give us 0Z or 0, and then we get 5 left. 8Z minus 7Z is 1Z minus 10. Add 10 to both sides, and Z is 15. So Z is 15. Then over here, we can subtract 3W from both sides. When we subtract 3W from both sides, over here we get 10. Over here we get 2W minus 30. Adding 30 to both sides will give us 40 equals 2W. Then getting rid of the 2, we divide both sides by 2, and W is 20. So we've now found both the variables. They've asked us to find the measure of angle B and C. So the measure of angle B was 5W minus 30 degrees. Substituting in the value of W, which is 20, we get 5 times 20 minus 30 degrees, which gives us 100 minus 30 degrees, which gives us 70 degrees for the measure of angle B. And of course, the measure of angle D is also 70 because opposite angles are congruent. Now for the other angle, that was B, the measure of angle C they asked us for, here was 8Z minus 10 degrees. Substituting in the value of Z, which is 15, we have 8 times 15 minus 10 degrees. Multiplying first, we get 120 minus 10 degrees. And that gives us 110 degrees for the measure of angle C. And of course, angle A is 110 degrees also. Example 6. Can you prove that the quadrilateral is a parallelogram based on the given information? If so, state your reasons to justify why. If not, explain. Here we have quadrilateral ABCD, and we're given information about it that we're going to go ahead and label our drawing with. The length of AB is 5. The length of CD is 5. The measure of angle A is 50 degrees. And the measure of angle D is 130 degrees. We want to prove that quadrilateral ABCD is a parallelogram. Well, we have several properties that help us do that. We've also got the definition of parallelogram. We won't be using the definition because the definition only involves parallel opposite sides. So we take a look at what we have. We notice that we have one pair of opposite sides that are congruent. We also have two angles that are not opposite each other. They're consecutive to each other, next to each other or adjacent. And we know something about consecutive angles and we know something about opposite sides. But when we've got one pair of opposite sides congruent and we've got one pair of consecutive angles supplementary, can we show that we have a parallelogram? We can, by the property or theorem that says that if one pair of opposite sides of a quadrilateral is both congruent and parallel, then it's a parallelogram. But also, we've got these consecutive sides that are congruent, showing that these two sides will be parallel. So starting with the fact that these two angles are supplementary, it causes these two sides to be parallel to each other. Now that goes way back. If two lines are cut by a transversal so that consecutive interior angles are supplementary, then those two lines are parallel. So we can show that these are two parallel lines first. So to start off with, we say yes, this can be proved a parallelogram by, that was a converse. It was the same side, interior angles converse, which again tells us that if two same side angles or consecutive angles of two lines cut by a transversal are supplementary, 130 plus 50 is 180, then these two lines must be parallel. So we write that out. Since 50 degrees plus 130 degrees is 180 degrees, and AB must be parallel to BC. So we now know that these two are parallel. Also, since one pair of opposite sides are congruent, since AB is equal to CD, 5 equals 5. Those are congruent sides. Now we've got one pair of congruent opposite sides and we've got the same two sides parallel. So now we can say, so by the property that states that if one pair of sides, AB and CD, are parallel and congruent, AB is congruent to CD, which we just showed up here, then it's a parallelogram. ABCD is a parallelogram. Example 7. Determine whether quadrilateral ABCD in the graph is a parallelogram or not by using a property of parallelograms. Now that opens us up to many different choices, including the definition of parallelogram, because that's a property also. Several different ways we could do this. I'm going to try to do it the simplest way we can. We could show that opposite sides, both pairs of opposite sides, are congruent, but we'd have to use the distance formula. That's quite a bit of work. We could also show that these two sides are parallel and the same two sides are congruent by using the distance formula. That's also a little bit of work. But what if we use the definition of parallelogram, that opposite sides are parallel, both pairs of opposite sides are parallel? Well, recall back when we talked about parallel lines in the coordinate system, their slopes must be equal. For instance, line BC and line AD, if you were to extend these, are parallel if their slopes are equal, and the same with CD and BA. So if we can show that or verify that, then we can call ABCD a parallelogram. So, by definition of a parallelogram, we're going to try to find the slope of AB, and it should be equal to the slope of CD. And same with the other two sides. The slope of BC should be equal to the slope of AD. Recall the slope formula in general is y2 minus y1 over x2 minus x1. It's been a while. So let's get these ordered pairs. We have ordered pair A, point A. Let's see, that would be -5, 0, -5. B is at -6, -4. C is at -2, 4. And D is at 4, 3. Okay, so using the slope formula here, here, and then here and here, we see if this really is a parallelogram. So starting with AB, these two right here, I'm going to let A be my first point, B be my second point, using this formula here, starting with -4. So I use the formula y2, -4, minus -5, over, back over to here, -6, minus 0. And we're going to see if that's equal to the slope of CD, using these 2 points, letting C be my first point, D be my second point. I start with 3. That would be 3 minus y1, 4, over, back over here, 4, x2 minus x1, which is -2. So we work this out on the left side and the right side to see if they're the same. -4 minus -5 is -4 plus 5, over -6 minus 0 is -6, equals 3 minus 4 is -1, 4 minus -2 is 4 plus 2. Further simplifying, -4 plus 5 is 1 over -6, and then we have -1 over 4 plus 2 is 6. Remember, the negative sign in a fraction can be placed in the numerator, the denominator, or it can be placed in front of the fraction bar. So these are equal to each other. So we've shown that the slope of AB is equal to the slope of CD. AB and CD are parallel. So AB, therefore, AB is parallel to CD. Now we need to prove the same thing with the other two sides. So I'm going to start with BC, these two right here, starting B is my first point, C is my second point. So I'm going to start with y2. So that would be 4 minus -4 over, and back over here, -2 minus -6 equals the slope of AD. AD, these two right here. A is my first point, D is my second point. Starting with y2, which is 3. We have 3 minus negative 5 over, back over here, 4 minus 0. Simplifying on the left and right sides, we have 4 minus negative 4 is 4 plus 4, and negative 2 minus 6, negative 6 is negative 2 plus 6. 3 minus negative 5 is 3 plus 5 over 4 minus 0 is 4. 4 plus 4 is 8. Negative 2 plus 6 is 4. 3 plus 5 is 8 over 4. And then, of course, 8 fourths reduces to 2 over 1, or 2. And since 2 does equal 2, the slope of BC is equal to the slope of AD. Therefore, side BC is parallel to side AD. So since these are parallel, and these are parallel, both opposite sides, pairs of opposite sides are parallel, this is a parallelogram.